On the incline, the steepness is the ratio of the change in elevation to the change in horizontal distance. This ratio, a number, is called the slope. For example, suppose the elevation of an incline increases 15 meters every 100 meters. The rider moves upward 15, horizontally 100. The slope is 0.15. A hill with a slope of 0.3 is twice as steep as one with a slope of 0.15. The bigger the slope, the steeper the hill. When the slope is large, it's no small feat to get to the top. When the slope is next to nothing, near zero, it's easy going. And when the slope is negative, it's downhill all the way. Although mathematics can be easygoing, it does have its peaks and valleys. And it always has. Nobody knows who first asked the best way to get from here to there. But the answer, in algebraic terms, was first offered by a French mathematician named Fermat. In 1629, he came up with the idea of finding the tangent line to an arbitrary point on a curve. In 1638, Fermat shared his discovery with his countryman, René Descartes, who had his own method for finding tangents to algebraic curves. Many of these mathematical ideas, especially those of Fermat, were further developed by Wilhelm Leibniz and Isaac Newton into a general and systematic method of mathematical analysis, differential calculus. Setting history aside, at least for the present, some timely questions remain. For example, on a smoothly changing curve, there's a constantly changing slope. How then, in today's language, is a slope calculated at any given point? To determine the slope at a particular point, here for example, simply take another point on the hill. It doesn't matter where. Now connect the 2 points with a straight line. That line is called a chord, and its slope depends on the location of the second point. If the first and second points are reasonably close, the chord is a reasonably good approximation of the bike's path. Now, move the second point closer to the first. Move it even closer. The slope is a number, and as the points get closer together, the number gets closer to a certain value. It's reasonable to call that number the slope of the hill at that point. The line with that slope through the point is called the tangent line. And the tangent line is just what the chord turns into as the points get closer together. And the slope of the tangent line at that point is the slope of the hill. Instantaneous speed can be calculated along the same lines. Galileo's law of falling bodies, applied here to a rather reluctant one, is more than an experiment in terror. It's differential calculus to the rescue.
Change in distance is divided by change in time. The ratio is the average speed during a given time interval. When that time shrinks to zero, the limiting value of the average speed is the instantaneous speed. Change in elevation is divided by change in horizontal distance. The result is the slope of a chord joining 2 points. When the horizontal distance shrinks to zero, the limiting value of the slope of the chord is the slope at that point.
Differentiation. The goals and calculations differ, but not the essential concept nor the process. Speed is the derivative of distance with respect to time. Slope is the derivative of elevation with respect to horizontal distance. In any case, a derivative is what happens to a quotient, a ratio of two numbers, as both top and bottom shrink to zero. Before they actually reach zero, small numbers are marked by the Greek letter delta. Delta y is a small change in y. Delta x, a small change in x. So delta y over delta x is merely a ratio of two small numbers. When the small numbers shrink to zero, that ratio becomes a derivative, and the deltas become a new symbol, dy over dx, the symbol of the derivative, which means the derivative with respect to x of the quantity y.